Hey there, y'all. Today we're going to look at 7.2 on adding and subtracting rational expressions. In this section, you're going to be able to determine the least common multiple polynomials and be able to add and subtract rational expressions. We continue with the same two standards that we looked at in 7.1. That's ACE.1, again dealing with solving equations and inequalities in one variable, and then the pre-calculus standard, being able to understand rational expressions and closing them under addition, subtraction, multiplication, division, and so on. So again, we're kind of right on the edge of this is Algebra 2 and this is pre-cal, but we're looking at this together. All right. So what is a rational expression? Remember, we talked about that rational expressions are just fractions. So what's required to add or subtract a fraction? You've got to have a common denominator. And so with regular fractions, how would you get a common denominator? It's the least common multiple. Now, if we had like 2 and 3, we know we multiply and get 6, right? But when we've got numbers that contain like factors, we're going to do something a little bit different, right? So we talk about getting our list of 8 and our list of 14. And so 8, 16, 24, 32, 40, 48, 56, 64, 72, 80, and so on, right? And we can continue to list as long as we need to go. We do the same for 14, 28, 42, 56, 70, and so on. And we see on both of those lists, 56 is the first number that is on both lists. And so this fraction would eventually become over 56 and over 56, right? And we have to ask ourselves, what would we multiply the 8 by to get to 56? Well, we would take the 8 and we multiply it by 7. Well, that means I have to multiply the 3 by 7 and get 21. And then we come over here to the 14. Well, 14 times 1, 2, 3, 4 is 56. So 3 times 4 is 12. And we're able to add those together. Now, I want to show you one step that we don't normally show, but it is a property that we need to understand for what we're going to do later in this section. One step that we need to talk about is when we combine fractions through addition or subtraction, we're really combining them into one fraction and then doing the operation. And so we would write 21 plus 12 as the numerator and then 56 as the sole denominator in this. And then we can add these together and get 33 over 56. This doesn't reduce, so we're done there. Okay. So again, think about how we add and subtract fractions, what's going to happen, and we're going to look at some examples here on how to get that. So let's look at example 1. So in example 1, we're looking for the least common multiple of these three polynomials. And what has to happen is we need to look at the prime factorization of each of these and understand what terms they have in common. Now I'm going to show you a way to simplify this and kind of organize your work. And there's different methods that you can find out there. But I think this one works well in understanding how least common multiples actually work. So we're going to list out our three numbers. We've got 15 a squared b c cubed. We've got 16 b to the 5th c squared. And we've got 20 a cubed c to the 6th. And we're going to break this up into its prime factors. So what times what gives us 15? Well, that's 3 times 5. Now, the variables, we'll spread them out a little bit, but we have them all still written out. And we're going to leave the powers on them. We're not going to write like a times a times a. We want to leave the a's together, the b's together, and the c's together. 16, what does that break up to? Well, 16 is 4 times 4, but that's not the prime factorization. 16 actually breaks down to 2 to the 4th because the 4 will break up to 2's, and this 4 breaks up into 2's, right? So it's 2 to the 4th, and then I've got b to the 5th and c squared. Okay, so again, we want to start lining these up based on the bases, okay? And finally, the 20. What does 20 break up to? Well, 20 is 2 times 10, and then 10 breaks up to 2 times 5, so I've got two 2's, so that's 2 squared. And I've got a 5, and then I've got an a cubed and a c to the 6th. And again, we want everything lined up because now we're going to drop these down. And we're going to take the highest exponent of each base that is in this problem. And so the first base is 2. and its highest exponent is 4, so we got 2 to the 4th. There is a single 3, so we've got to bring it all the way down and through. There's a pair of 5s here, but neither have a power, so we'll just have a 5. In the a's, we got a squared and a cubed, so that's going to be the higher power, so that's a cubed. B and b to the 5th, so that's b to the 5th, again, higher power. And finally, we've got 3, 2, and 6 for the powers of c, so we take the highest, and that's 6. And so this is least common multiple. Now, we need to multiply back the number part so we can know, a normal coefficient out there instead of seeing 2 to the 4th times 3 times 5. I mean, none of y'all are going to be like, oh, that's this number. No, I know that. So what is 2 to the 4th? 2, 4, 8, 16, right? So 16, and 3 times 5 is 15, and then 16 times 15 is 240. And then everything else is just going to trail behind. A cubed, b to the 5th, c to the 6th. This is the least common multiple of these 3 monomials. Okay? Again, the biggest key here, right here, you need the highest exponent of each base. If you keep that in mind, everything else is going to be easy as we go through these problems. Okay? So let's look at example B, where we're going to deal with some non-monomials, some polynomials, that have some terms that we need to factor out. So in this one, we've got x cubed minus x squared and minus 2x. And so again, how can that factor out? Well, I can first factor an x out of it, right? And that's going to give me times x squared minus x minus 2. Now that's a quadratic that's going to x puzzle. So we'll x puzzle this, negative 2 and negative 1. So that's going to be a negative 2 and a positive 1. So this is going to become x times x minus 2 and x plus 1. We do the same for the x squared minus 4x plus 4. That one's just going to x puzzle. 4 on top, negative 4 on the bottom. So what's going to multiply to 4 but add to negative 4? That's negative 2 and negative 2. So that's going to be x minus 2 times x minus 2, or just x minus 2 squared. Now, like we did before, we can line these up over here. And so I've got an x minus 2, and an x plus 1 from the top. And then I've got an x minus 2 squared from the bottom. Again, we're going to drop everything through and take the highest exponent of what matches. So we've got an x. We've got an x plus 1, and then here I've got an x minus 2, but I've also got an x minus 2 squared, so I'm going to take the 1 with the square because I take the higher power. And all these are multiplied together, and this is the least common multiple of these two polynomials. Now, this is going to come out to a 4th degree power, and that's fine if we multiply this all back out. That's fine that we get that. We are going to have to go to higher powers when we do these. Okay, so now what we're going to look at in the next examples is how to actually add and subtract these together by finding these common denominators. So in this example, we're dealing with monomial denominators. And when we're trying to get a common denominator, remember, we're only going to focus on the denominators, and then we'll get back to the numerators and have to multiply them by something. So we're going to do what we did in example 1 and write out our list and figure out how does 5b factor out and how does 10a squared b squared factor out. Well, 5b is just 5 times b. And then 10 is going to break up to 2 times 5. So 2 times 5. And then I've got an a squared. I didn't leave myself enough space, so we'll just put it out here, a squared. And then I've got a b squared. The order when you're doing this doesn't really matter as long as everything's lining up in their own columns. When we finish it off, we'll kind of get it sorted back together, or the coefficients will multiply back into 1, and we'll get the variables back in alphabetical order. So, dropping everything through, we've got a 2, we've got a 5, we've got a b squared, and we've got an a squared. And this is going to be 10 a squared b squared. Now, here is where the change comes in. Because if we're just looking for the least common multiple or the least common denominator, that is the least common denominator. But now we have to ask ourselves, what parts are missing from each of these denominators? Well, this denominator is a match, right? So we're not going to have to do anything with the second fraction. but we are going to have to do something with the first fraction. What pieces am I missing on this first line that I have down here on the last line? Well, it's missing a 2, so I'm going to have to times this by 2. It's b squared, but I only have a b, so I'm going to have to multiply it by a b. And I don't even have any a, so I have to get the entire a there. So I'm going to take this fraction, and I got to multiply the numerator by 2a squared b, and the denominator by 2a squared b. And so we need to multiply that out. And so 2 times 7 is 14. I had a squared and a squared. That's going to give me a to the 4th, and there's a b. This is going to be over 10 a squared b squared, multiplying that to get our common denominator. And then plus the 9 over 10 a squared b squared. So now I've got this where I have the same denominator. And so the two fractions now become 1 through addition. And so what we're going to get is 14 a to the 4th b plus 9, because plus 9, all over 10 a squared b squared. Now, if everything could reduce, we would reduce, right? If everything, like all three of these had a factor of 2 in them, we'd all divide it by 2. But that would have been found up here, actually. Normally, that's going to cancel itself out early on. But again, you can get some cases sometimes where something factors out or something reduces and it comes out. But not always, okay? So that is how we get this with monomials. The next example, example 3, is going to be looking at polynomials and how we factor that out to get the pieces that we need. All right, in example 3 here, we've got x plus 10 over 2x minus 10 minus 4x plus 8 over 7x minus 35. Again, we're going to start this problem looking at our denominators. We're not even going to look at those numerators. We don't care about them yet. So 2x minus 10, how can I factor that? Well, that's going to be 2 times x minus 5, because factoring out the 2, that's all we can do. And then the 7x minus 35, we can do the same. We can do 7 times x minus 5. And so when we write our list out over here, we've got the 2 times the x minus 5. And this one has a 7 times the x minus 5. And so what's going to fall through to get our common denominator? Well, we've got the 2, we've got the 7, and we've got an x minus 5. None of them have power, so they just fall straight through with what they are. Okay. Now, we come back and we ask ourselves, okay, now that we know what we need, what is missing from each of these lines? And so this has the 2 and has the x minus 5. It's missing what? The 7. And this line has the 7 and it has the x minus 5, so it's missing what? The 2. So this fraction, top and bottom, numerator, denominator, will get multiplied by 7. This fraction, numerator and denominator, will get multiplied by 2. And so when we do that, what we're going to get, distributing this in, 7x plus 70 over 2 times 7 is 14, so we can simplify that a little bit, 14 times x minus 5, minus multiplying 2 to both of those. Now, here's one step where we'll do this in 2 steps, and I'll talk about how we can get in one step as well. So we're going to get 8x plus 16 over 14x minus 35. Now, what also has to happen is this minus sign distributes to both of these to become one fraction. And so we're going to get 7x plus 70, distributing the negative, so minus 8x minus 16 all over 14x minus 35. Now, we combine our like terms in that numerator. We're going to get negative x plus 54 all over 14x minus 35. The denominator, again, we could factor that 2 times 7, but none of those are common factors to anything in the numerator that we could factor out. And so this problem's done. I mean, we could do some cleanup and some different things to change the order of things and not have a negative sitting in front of that x and everything else, but there's no need, okay? That whole rambling, just ignore it. This is our answer. Okay, so again, if we're looking at polynomials, we want to factor them to all their little pieces. Even if we've got like a quadratic or a cubic, we want to factor it down and get to our final simple denominator. Okay, we got one more example we're going to look at. I know the notes are going to see example 4 and example 5, but I've decided just to stop at example 4 because the two examples that are down there, there's two different methods, but I'm going to show you one method for this that works every time, and I want you to focus on that method. So let's look at example 4. In this example, we have a complex fraction with different least common denominators. And so what we're going to do is we're going to focus on each of the fractional parts. We're going to focus on the numerator here and the denominator here, get them settled so that we can make it one fraction for each piece, and then deal with, remember that this is a fraction in a fraction, right? It's a complex fraction. And so this is division, right? So we've got to rewrite this as a division problem at some point. Well, we're actually going to do that in step 1 and then start moving things around so it's less complicated. So starting with the top here, m over n minus n over m, all that's in a parenthesis, divided by n over m plus 2. So we've got our two pieces separated out. Now we're going to work on the first parenthesis and get it as one fraction. And so what we're going to see, well, what's the common denominator here? Well, like a simple problem, right? This needs the m, this needs the n. So this is going to multiply by m to both, and this is going to multiply by n to both to get mn as the denominator. So getting that, mn. This is m times m, so that's m squared. This is n times n, so that's n squared, and there's a minus in between. So the first fraction's already done, actually. Now, the second one's actually pretty easy, too, because remember that this 2 is over 1, so the common denominator is just the thing that's not 1, so it's m. So I'm going to multiply this by m and this by m. So in the second fraction, we're going to get n plus 2 times m, so 2m over m. This is still division. Now we've got to take our division and, of course, change it to what? Multiplication. So m squared minus n squared over mn times, taking the reciprocal of this fraction, m, and we don't need the parentheses anymore, over n plus 2m. Now, if any of this would factor, we would factor it. And actually, this piece is a difference of squares, so I could rewrite it as m minus n times m plus n, right? And there's almost a piece that matches, but this one doesn't, right? It's really close, but it doesn't. Times the m over n plus 2m. So is there anything that's going to cancel in this? Actually, the answer is yes. This m is multiplied to the n. This m is multiplied just to the rest of the numerator. So it is a common factor. So the m's in this problem will actually cancel here and here. And so our final answer, multiplying this out, we're going to get m minus n times m plus n over n plus 2m, or you can flip the order of that if you want to have the m first. So 2m plus n. So that's it on this video. Again, there's another example, but it's exactly the same like this one. It's a different method, but if you focus on this method, it works for every problem. So that's it for today. Make sure you work on your assignment. Make sure you get it turned in. And if you need me, you know how to contact me. Hit up that email or hit the Google Classroom and submit a note in there. So that's it. I hope y'all are staying safe, and I'll catch y'all next time.